Welcome back. Today's topic is, in my view, the single most important result in a first calculus course, the Fundamental Theorem of Calculus, both halves of it, the 200-year argument over who discovered it and what it really means, and a handful of worked examples so you can actually use it. Here's what I want you to leave with. Most students meet this theorem as a piece of textbook magic, some formula, capital F of B minus capital F of A, that just appears one day. It isn't magic. It's the one identity that links every derivative you ever took in differential calculus to every integral you're about to compute. Same object, two angles. Put the two definitions side by side and ask yourself whether they look like they belong to the same subject. The derivative of f at x is the limit, as h goes to 0, of f of x plus h minus f of x, all divided by h. That's a statement about slope. You take 2 points on a curve, draw the secant between them, and slide them together. The number you get in the limit is the slope of the curve at x, the instantaneous rate of change. The definite integral of f from a to b is a completely different procedure. You chop the interval from a to b into n little pieces of width delta x, pick a sample point inside each piece, multiply function value by width, add them all up, and then take a limit as n goes to infinity. What you get is the signed area between the curve and the x-axis. One's about slopes, the other's about areas, and nothing in either definition says they should be related. And yet, they are. Tightly. The first person to really see that derivatives and integrals were inverse operations was Isaac Barrow, Cambridge professor, 1660s, holder of the Lucasian chair of mathematics, the same chair that would later belong to Newton, then Babbage, then Dirac, then Hawking. Quite a lineage to start with. In his Lectiones Geometrically, published in 1670, Barrow proved, in purely geometric language, what we now call the Fundamental Theorem of Calculus. Translated into modern symbols, his result reads, if capital F of x is the area under a curve f from some fixed starting point up to x, then the slope of the tangent line to capital F at x is equal to f of x, slope of the area function equals the height of the original curve. That is exactly the modern theorem. But Barrow stated it as a fact about figures, lines, and tangents. He did not have algebraic notation for the derivative or the integral. He could not write capital F prime equals little f. His Cambridge successor in the Lucasian chair could. So could, independently, a German lawyer named Leibniz. Newton got there first, chronologically. In the late 1660s, holed up at Woolsthorpe Manor during the plague years, he developed what he called the method of fluxions. In his language, a fluent is what we call a function, and its fluxion is what we call its derivative. An antiderivative is a fluent whose fluxion is the original function. He knew differentiation and integration were inverses. He used the idea to derive power series for sine, cosine, and the logarithm. And then, in a decision that would cost him dearly, he sat on most of this work for decades. Meanwhile, on the continent in 1675, working with no knowledge of what Newton had done, Gottfried Leibniz reached the same conclusion. He also invented the notation we still use 3.5 centuries later. That elongated s we call the integral sign? Leibniz's. He picked it because the integral is a sum. The d in dx? Also Leibniz. He wanted the symbolic algebra of infinitesimals to look natural on the page, and dx did the job. Crucially, Leibniz published. He started in 1680-something in a journal called Acta Eruditorum, Acts of the Erudite, and so on the continent, calculus was Leibniz's calculus before it was ever Newton's. You can imagine how that went over in England. It went over badly. Around 1710, the dispute boiled over. Each side accused the other of plagiarism. The Royal Society, where Newton happened to be president, convened a committee to investigate. The committee ruled in Newton's favor. Newton wrote the committee's report himself, anonymously. I'll let you sit with that for a second. The fallout lasted a century. British mathematicians stuck with Newton's awkward fluxion notation out of national pride and watched the continent run laps around them in analysis for the next 100 years. The theorem itself, of course, did not care who got the credit. Differentiation undoes integration. That was true in Cambridge, and it was true in Hanover. Here is something that surprises people. For almost 150 years after Newton and Leibniz, mathematicians used the fundamental theorem confidently. They produced one brilliant result after another with it. They could not have told you what an integral actually was. The definition just was not there yet. Cauchy was the one who closed that gap. In his lectures at the École Polytechnique in Paris during the 1820s, he gave the first widely influential rigorous definition of a definite integral for continuous functions as a limit of partition sums. Clean, careful, modern in spirit. A generation later, the German mathematician Bernhard Riemann pushed it further. In his habilitation thesis of 1854, Riemann generalized Cauchy's construction in what looks like a small move and turns out to be a deep one. He allowed arbitrary sample points inside each subinterval, and he asked the question, does the limit exist as the mesh of the partition shrinks to 0, no matter how you sampled? If yes, the function is integrable. This pinned down exactly which functions admit an integral, including, importantly, some functions with discontinuities. That is the modern Riemann integral. And only once Riemann's definition was in place could the fundamental theorem of calculus be proved as a theorem rather than treated as a guiding principle. So that one-line identity you'll write at the end of this video is basically four mathematicians stacked on top of each other. Here is the first half. Assume f is continuous on a closed interval from a to b. Build a brand new function out of f, call it capital F of x, and define it as the integral of f of t dt from a up to x. In plain English, capital F of x is the running total of signed area under f, starting at a and stopping at wherever x happens to be. The upper limit is the input. The theorem says two things. Capital F is differentiable on the open interval from a to b, and its derivative is f itself. Integrate, then differentiate, and you land exactly where you started. One bit of vocabulary we're going to use constantly from here on. An antiderivative of f is any function whose derivative is f. If capital F prime equals little f, then capital F is, by definition, an antiderivative of f. Part 1 has just told us that the running area function, the accumulation function, is one specific antiderivative of f. That is a stranger claim than it looks. Pause on it. Areas under a curve, computed as a limit of Riemann rectangles, are differentiable objects, and when you differentiate them, you get back the curve you started with. The integral sign earns its place next to the derivative sign right here. Part 2 is the half you'll actually use to compute things. Same setup, f continuous from a to b. Let capital F be any antiderivative of f, any function with derivative equal to f on that interval. Then the integral of f from a to b is simply capital F of b minus capital F of a. Read that again because it's doing a lot of work. Instead of falling back to Riemann's sums and limits every single time you want an area, you find an antiderivative, plug in the two endpoints, subtract, and you're done. The whole integration problem collapses into the anti-differentiation problem. That's why most of the rest of this playlist, substitution, integration by parts, partial fractions, trigonometric tricks, is really one long catalog of ways to find antiderivatives. Look at how the two halves snap together. Part 1 promises you that for any continuous function, you can construct an antiderivative simply by integrating it. Part 2 says that once you have any antiderivative in hand, you can use it to compute definite integrals by subtraction. Part 1 builds, Part 2 cashes in. In practice, you'll reach for Part 2 almost every time you compute an integral, and you'll reach for Part 1 when somebody hands you a function defined as an integral and asks you to differentiate it. Two different moves. One single idea, that integration and differentiation are mutual inverses. Why is Part 1 true? The proof is short, and the picture is genuinely satisfying, so I want to walk through it. We want the derivative of capital F at x. By definition, that is the limit, as h goes to 0, of capital F of x plus h minus capital F of x, all divided by h. Look at that numerator. It's the difference of two integrals, both starting at a1 stopping at x plus h, the other at x. So the numerator is just the integral from x to x plus h of f of t, dt. The big area minus the smaller area is the thin sliver in between. Capital F of x plus h minus capital F of x is the area under f over a tiny slice between x and x plus h. Now we use a small but useful side result called the mean value theorem for integrals. It says that if f is continuous on a closed interval, then somewhere inside that interval, f hits its own average value, so the integral over the whole interval is equal to that one value times the width. Average times width. Apply that to our sliver. There exists some point c in the closed interval from x to x plus h where the integral over the sliver is exactly f of c times h, the width. Divide both sides by h. The difference quotient is just f of c. Now send h to 0. The sliver collapses. The point c is squeezed against x. Because f is continuous, f of x. So the derivative of capital F at x equals f of x. That's the whole proof. And if you squint, what you just saw is Barrow's geometric picture written out in algebra 3.5 centuries later. First example. Compute the integral from 0 to 2 of x squared dx. First, we need an antiderivative of x squared. The power rule for derivatives says the derivative of x to the n is n times x to the n minus 1, so running that backwards, an antiderivative of x to the n is x to the n plus 1, divided by n plus 1, as long as n is not negative 1, since dividing by 0 is rude. For x squared, that gives x cubed over 3. Now hand it to the Fundamental Theorem Part 2. The integral from 0 to 2 of x squared equals the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Plug in, 2 cubed over 3 is 8 over 3, and 0 cubed over 3 is 0. 8 over 3 minus 0, 8/3. Done. And we didn't touch a Riemann rectangle, or a limit, or a sum. One antiderivative, one subtraction, done. That's the trade the Fundamental Theorem is offering you. Don't take my word for it. You can verify the answer by grinding out the Riemann sum directly. write endpoint sum with n equal pieces. The sample point in the ith piece is 2I over n. The function value at that sample is 4I squared over n squared. The width of each piece is 2 over n. Add those up from I equals 1 to n, and the constants pull out front, you get 8 over n cubed, multiplying the sum of I squared from 1 to n. And that sum, conveniently, has a closed form. N times n plus 1 times 2n plus 1 all over 6. Multiply through, take the limit as n tends to infinity, watch the lower order terms die, and what survives is 8/3. Same answer. One way took a subtraction, the other took a page. Take the subtraction. Here's an example designed to show off part 1. Compute the derivative with respect to x of the integral from 2 to x of sine of t squared dt, now sine of t squared. That integrand is famously awful. It has no elementary antiderivative, meaning there is no finite combination of sines, cosines, exponentials, polynomials, logs, and the rest that you can differentiate and get sine of t squared. If I asked you to evaluate this integral, the honest answer is you can't, not in closed form. But we're not being asked to evaluate it, we're being asked to differentiate it with respect to its upper limit. And the Fundamental Theorem, part 1, hands us the answer immediately. Just plug the upper limit into the integrand. The derivative is sine of x squared. That's the whole computation. No antiderivative required. You just differentiated an integral that, frankly, nobody can compute in closed form. Part 1 let you do that. Before we move on, that word continuous in hypothesis is doing real work. Both halves of the fundamental theorem ask for f to be continuous on the closed interval, and it's worth seeing what happens when that assumption fails. The theorem stops applying, and you can watch the whole thing break in slow motion. Here's the cleanest counterexample I know. A step function, f equals 0 on the interval from 0 up to, but not including 1, and f equals 1 from 1 through 2, one jump right at x equals 1. Compute the accumulation function capital F directly, by hand. From 0 to 1, the area under f is 0. From 1 to some x between 1 and 2, the area is just the rectangle, width x minus 1 and height 1, so the area is x minus 1. So capital F is the piecewise function, 0 on the left half, x minus 1 on the right half. Notice that capital F is still continuous everywhere on the interval. Integration is a smoothing operation. The jump in f got filed down into a corner in capital F, but the corner is at least continuous. Here's the problem, capital F is not differentiable at x equals 1. The left-hand derivative at that point is 0. The right-hand derivative is 1. They disagree. A derivative needs both sides to agree, so capital F prime of 1 doesn't exist. The equation capital F prime equals f cannot possibly hold at the jump, because the left side isn't even defined. That's why the hypothesis matters. And it's also a preview of what we'll need later. Once we start looking at really pathological functions in real analysis, we'll have to bring in stronger theories. Lebesgue integration, most famously, to keep a version of this theorem alive. Sine x is the one you should be able to do in your head. Compute the integral from 0 to pi of sine x dx. An antiderivative of sine x is minus cosine x. Quick sanity check by differentiating. Derivative of minus cosine x is sine x. Good. Now, part 2. The integral equals minus cosine of pi minus cosine of 0. Walk it through. Cosine of pi is minus 1, so minus cosine of pi is plus 1. Cosine of 0 is 1, but it carries a minus sign in front of it, and then there's another minus from the subtraction, so the double negative turns into plus 1. Add them, 1 plus 1 is 2. The area under one full positive hump of the sine curve, from 0 to pi, is exactly 2. There is something a little magical about that. A transcendental function, defined by its own peculiar power series, irrational at almost every rational argument, and yet you integrate it over its first arch and you get the integer 2. Clean. Last example. Compute the integral from 1 to e of 1 over x dx. An antiderivative of 1 over x is the natural logarithm of the absolute value of x. On the interval from 1 to e, x is positive, so we don't need the absolute value, and our antiderivative is just log of x. So by part 2, the integral is log of e minus log of 1. Log of e is 1, by the definition of e. Log of 1 is 0, so the integral is 1. Think about what that sentence actually says. The area under the hyperbola y equals 1 over x between x equals 1 and x equals e is exactly 1 square unit, not approximately. Exactly. In fact, this is a perfectly good modern definition of the number e. It is the unique number greater than 1 such that the hyperbolic area from 1 to that number, computed under 1 over x, is equal to 1, a transcendental constant pinned down by an area. And the fundamental theorem reduced what could have been a hideous geometry problem to 2 log values and a subtraction. I call it the Fundamental Theorem. The name is bold, and it earns the boldness. Barrow saw it in pictures. Newton, Leibniz, Cauchy, and Riemann then spent 2 centuries arguing about how to write it down. What they all converged on is the same single statement. Areas and slopes are 2 views of the same underlying object. Part 1 guarantees that every continuous function has an antiderivative. Part 2 makes integrals genuinely computable in practice, not just definable in principle. Together, they are the reason the rest of this playlist is really just a long tour of techniques for finding antiderivatives. U substitution, integration by parts, partial fractions, trig substitution, and so on. They are also the reason differential equations are a sensible subject at all. Given a derivative, integration lets you try to recover the original function. Every other result in integral calculus is built on top of this one theorem. But it goes further. Once you start generalizing the integral, to Lebesgue's version in real analysis, to contour integrals in complex analysis, to line and surface integrals in vector calculus, there is always a fundamental theorem hovering nearby. The fundamental theorem of line integrals is part 2 for vector fields. Green's theorem, Stokes's theorem, the divergence theorem, all of them are higher dimensional descendants of the same identity. Learn this one well, and you've basically met every fundamental theorem that comes later. They all rhyme with it. So, Barrow first, in 1670, geometrically, before anyone had algebraic notation for the derivative or the integral. Newton and Leibniz then rediscovered it independently in modern symbols, and decades later, their followers, and eventually the 2 men themselves got dragged into a vicious priority dispute over who deserved the credit. Cauchy in the 1820s and Riemann in 1854 finally pinned down a rigorous definition of the definite integral, which let this be proved as a theorem rather than treated as a principle. Part 1, the derivative of the accumulation function from a to x is the original function. Part 2, any antiderivative lets you compute a definite integral by one subtraction. 4 examples. A polynomial integral done by power rule. A derivative of an integral whose integrand has no elementary antiderivative. The area under one bump of sine equal to 2. And the area under 1 over x from 1 to e equal to 1, which is a perfectly good definition of the number e. Next video, we get to the technique that squeezes the most mileage out of part 2, integration by substitution. See you there. Just as the fundamental theorem ties together 2 halves of calculus that looked totally unrelated, your likes and comments tie this channel together with the learners it was made for. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.